So we go now to the next presenter, which is Marco Ventoli. And Dr. Marco Ventoli received his master's in electrical engineering and PhD and postdoc in electrical and thermal energy from the University of Pisa, respectively, with a specialization in optimization and Monte Carlo simulation. Nowadays, he is a senior scientist at ABB Power Grids Research, Germany, working on power system optimization projects, although I think that maybe from today it is Hitachi, I'm not sure.
Yeah, exactly, this is the day one, yeah.
So thank you very much for being the first, maybe Hitachi presenter, Hitachi ABB Power Grids presenter, maybe. And this paper will be on the control of distribution grids with storage using nested Benders decomposition. Dr. Giuntoli, you have the floor. And this will actually be a presentation that is recorded. So if the host could play that, super. Thank you.
I think that doesn't work. Are you able to catch the audio?
Not yet. I'll have the host try again.
Yeah. Otherwise, I can try from my side.
I would say open the PowerPoint already, just in case.
Okay.
Ladies and gentlemen, good morning or good afternoon. My name is Marco Ventoli from ABB Power Grid Research, Germany. Together with the author Milos, Subasic, and Susanne Schmitt, we are proud to present the paper with the title Control of the Distribution Grid Unit Using Energy Storage with Nested Benders Decomposition. The presentation is divided in mainly 5 parts. First, the introduction, then the explanation of the formulation of the optimal power flow that has been used in this work, then the explanation of what is and how it's used in nested Benders decomposition, then the numerical results and the conclusion. New challenges in the distribution grid are present. Let's discuss about the rapid development of the new energy technology, like the renewable energy sources, for example, in terms of distributed generation, as well as electric vehicle charging. So, new challenges to the traditional distribution grid management are present. For example, the increased voltage level and short circuit current. They play an important role for changing the power supply reliability and power quality. Even important thing to take into account is the trend that is from the one-way to the multi-direction power flow inside the grid. So the installation of the energy storage system to back up and complete the available energy sources can play an important role. Along with an appropriate optimization model, they can decrease uncertainties of renewable energy limited predictability. Even the energy storage can increase the hosting capability of distribution grid by providing requested stabilization under high renewable penetration. So what we can do in order to reduce the risk of possible energy not supply and to increase the optimality of the distribution grid. So what is possible to use in the one of the fundamental widely used type of algorithm used for the control of transmission grid is the optimal power flow approach. The optimal power control of the energy storage cannot rely in only one snapshot optimization due to the multi-period constraints like a state of the charge related to the energy level. So, nested Benders decomposition is well-known technique for large-scale optimization problem, for example, hydrothermal scheduling or planning for transmission grid or for the high-size grid. So, what we can apply nested Benders decomposition to solve a nonlinear AC optimal power flow and distribution grid, take into account the multi-period and to tackle the time linking constraints phenomena due to the energy storage. A nonlinear multi-period optimal power flow problem for a time horizon t can be, in general, be formulated as the task to minimize an objective function that consists of the sum of objective functions for a single time step. One possible objective function is represented as the sum of generator dispatch cost for the time horizon t. Control variables are generator and storage set point, while the state variable comprise voltage magnitude and angle, active and reactive power flow over lines. In this paper, for each point in time, there is a set of inequality constraints, modeling the physical limits of grid components, such as the current limits of the line and the generator and storage variable bounds, as reported in the middle of the left side of the slide, with a g of x lower than 0 for all the time steps. In addition, there is a set of equality constraints for each point in time. The following equation describes the active power balance for all the nodes for all the time steps. In particular, here the subscript n, the node n. In the same way, for the real power, we can define the reactive power balance for the reactive part, where what we have in the bracket are related to the voltage magnitude and voltage phase angle for all the voltage present in the system. For a generic branch B and defining I as the node from and J, the node 2, it is possible to describe the relationship between the current and the voltage power using the equation in the matrix formulation on the right side of the slide. Exploiting the symmetry of the model, the matrix component will be with the subscript I is equal to the component with the subscript JJ, and in the same way, the component with the subscript IJ is equal to the component JI. Those values arise from the longitudinal and transversal substitutance and conductance parameter of each branch. The equations that describe the double bipole model are used to model the active and reactive power flow through the branches, and those flows are used inside the node's power balance in the previous equation. In contrast to the grid-related constraints described above, the presence of energy storage in the grid introduces time coupling constraints. In particular, the energy storage state of charge depends linearly on the state of charge in the previous time step, in the power charge and discharge form, as reported in the last equation, where S is the total amount of storage and T denotes each time step. This storage model could be further be extended to add in AC-DC converter losses, for example, then even to take into account the possibility for the converter to support reactive power for the voltage support ancillary service. Overall, the problem is nonlinear, non-convex, and each time step there is a linear coupling constraints between the time steps. In order to apply the nested bender decomposition, the time horizon is divided in P intervals, where the P+1 interval is considered as the slave problem of the P problem, or in the other way around, the P problem is considered as the master problem of the P+1 problem. By applying the recursion, this results in a chain of P optimization problem, as related in this picture, where the P problem, the objective function, is related to the local objective function of the P problem plus the future cost phi P. The future cost is all the costs related between the problem P to the end of the chain. In each iteration, basically, the nested benders decomposition apply in each subproblem some cutting plane. The cutting plane is a linear set of inequality constraints defined benders cuts, where in the left side is defined by the mu that is related to the dual variable, and B is related to the right-hand side of the equality constraints of the power balance energy equation. So on the left side, the sum is done by for all the storage. The P is the dual variable for the storage balance constraint for the slave problem P+1. The EPS is the final level of the energy storage for the problem P. So, and phi is the future cost for the right-hand problem. In general, the overall algorithm consists of two main parts for each iteration. The forward run, in order to solve all the sub-problems for the start to the end, while the forwarding the last storage energy level as the initial energy level of the next problem. Then the backward run solve all the sub-problem for the end to start while adding Bender's cuts. At the end of the forward run, an upper bound for the objective function is computed as the sum of the single objective function of the single optimal power flow without the future cost. And the other way around, during the backward iteration, a lower bound is computed, and the lower bound is defined as the objective function of the first sub-problem plus the future cost related to the other side. So the iterative approach is stopped when the lower bound and the upper bound meet the criteria. The proposed optimization scheme has been implemented in Python and using the Casati framework for interfacing the IPOpt solver for nonlinear programming. The numerical results are split in three different cases described below. Case A with the test feeder IEEE 13 nodes with the time horizon of 1 day. The case B with the test feeder IEEE 37 nodes with the time horizon of 1 week. And the case C with IEEE 123 with the time horizon of 1 week. The aim of the numerical test is to describe the behavior of the meter in terms of robustness, computational effort, and moreover, for each case study, several time division length of the decomposition method are shown and analyzed. For the case A, IEEE 13 nodes, on the left side, what we can see is the energy price with the early cadency and the total feeder demand in red. In the center, what is possible to see is the root mean square error between the holistic solution and the case B7. It means that we have 12 sub-problems and each problem is composed by 12 time steps for each iteration and storage. So the error you can see that decreased monolithically for both cases until we reach the iteration number 10. On the right side, we can see the energy level between the holistic solution after 10 iterations. For the storage 1, the results are identical for the first 8 hours. After that, a small offset is kept between the two solutions until the end of the day. In case of storage 2, the identical solution reached after 10 o'clock. For the case B, the test feeder IEEE 37 nodes for the time horizon of 1 week. The picture on the right side top shows the total feeder demand and the early energy price. The last one has been artificially modified on Wednesday and Thursday in order to have different daily results. However, for this case, the demand peak is reached during the weekend. And the bottom picture shows the energy stage of the storage number 1 after the last iteration, in case that we have 10 iterations. The holistic solution in blue, the Benders approach with a subproblem size of 504 hours in red and 3 hours in orange. The last test, the solution is not comparable with the holistic one, while the first test with 2 subproblems for 504 hours is similar to the holistic one except for a small deviation in the middle, exactly at the interface between the two subproblems where the Nested Benders decomposition passes information back and forth. The last case, case C, IEEE 133 has been analyzed with a 1 week of the time horizon. As in the previous case, 10 storages have been installed in the feeder with a total amount of energy of about 15 megawatt-hour. The picture on the right shows the value of the back and forward iteration for the lower and upper bound and the objective function for the KB7. Two monotone trends are clearly shown, while the upper bound reached practically the heuristic solution after 9th iteration. In this work, we apply the Nested Benders decomposition to multi-period and C, OPF, in order to control distribution grid with the storage system. This problem is nonlinear and non-convex, which means that there is no convergence guarantees for the methods. The case studies described above indicate that the method works and gives satisfying results after only a few iterations. The implementation of the approach demonstrates the possibility to more accurately control in distribution grid in presence of energy storage. However, there is a space of improvement. For computational efficiency of the subsequent execution of nested benders decomposition algorithm compared to the holistic optimization problem is still a suboptimal in terms of computational time. In terms of memory demand, the decomposition is favored due to the smaller problem size. So we assume that a bigger computational speedup can be achieved by the parallel execution of the subproblem. So the risk could be natural extension of this work. Moreover, the network control equipment can be completed, for example, by adding battery control that it can also allow to control the reactive power to support the voltage regulator. Additionally, the approach can be extended to include the integer variable and unbalanced three-phase grids. In the problem setting that presents here the only time coupling constraints, the storage balance constraints. The approach may as well be extended toward generation ramping constraints or other linear relationship between time steps.
Okay, thank you very much, Marco. So although this was a recording, we do have Marco here present to answer all your questions, or at least the ones that we highlight. So the first one is from Bruno, and he asked, thank you for the nice presentation. I was wondering if the approximated function by the Benders cuts is in fact convex. If they are not, any thoughts on the accuracy of the approximation?
Yeah, exactly. So good question. In case we are working on the space that are not so convex, we can stack in some suboptimal solution. In this case, the solution will be far away from the optimal solution that we get, like holistic one. This means that the Benders cuts, even being a linear cut, is not able then to evaluate the same solution that we get with the holistic one. And this one can be one thing that we have to take into account, because in this case we are running a completely nonlinear optimal power flow. So in case that we are moving far away from the linear behavior of the C system, we can stack in suboptimal of the objective function. And then we cannot reach the same optimality that we get with the holistic solution, just because the Benders cuts provide the linear cuts of the problem.
So I think a related question from Carlton, is the holistic approach finding the global optimum of this problem? It seems not given the non-convexities in the nonlinear model. So maybe.
The same for example, for the holistic solution, we apply the standard approach of the optimal power flow with the standard admittance matrix and the power flow injection model. So in this case, the equations are completely non-convex and nonlinear. And so again, for the holistic solution, we are not guaranteed the global optimum, but we are guaranteed the local optimum related to the shape of this function.
Okay, so we still have a few minutes, and we also have 3 more questions. So from Raoul,
sure.
we have also thanks for the nice presentation regarding the model of the battery. The author introduced the decision variables for charge and discharge power. How do you make sure that both are not non-zero at the same time? And do you use some approximations regarding this?
So yeah, for example, for the battery charge and discharge time, from what we did essentially is to use the charge for one variable and discharge for another variable, and after the solution we will check potentially if that we have some contemporary value that are different from zero in both cases. So as a workaround of this kind of problem, we set a very small cost related to the charging value in order to guarantee by tuning by hand that in the same time we are not going to charge and discharge in the same time the storage.
Okay, and another question from Raoul is we see that the holistic approach is much faster compared to the nested case. Can you please elaborate on the advantage of using the nested benders approach? So,
yeah,
I mean, you're not faster, so why are you doing it?
Yeah, exactly. Our intention was to find the breakthrough between the holistic approach and the decomposition approach. So we tested essentially the 3 case studies that we presented in this video, but essentially we not achieved the breakthrough in the way that we are not able to be faster than the holistic solution. Even, for example, for the last case, we have about 500,000 inequality constraints at variable. This means that the breakthrough for the nested benders decomposition is order of magnitude more. This means that we have to move to the, for example, bigger feeder, or maybe we have to increase the time length that we have inside the optimization. No, we cannot optimize only 1 week, but maybe we can go to 1 month or even 1 year, even if the stochasticity to optimize 1 week in the future it's so clear that it's not so clear. Yeah.
Okay. There are still some questions which we might deal with if we have time at the end, or you might answer them using the typed responses. But we have to stop here because I've been ordered to be very strict with time, and I will. So thank you very much.
Thanks, Chairman. Thanks, Chairman.